Hello. I think we are here, but oh my god, my character isn't talking. It's not alive. She looks dead, and I'm sorry about that. I don't really know what's the reason. Everything seems so messed up. I don't know if I should move on. Oh, okay, I see some movement, and it's really horrible. She's trying, okay? I think we should give her that. She's trying. I wasn't sure if I can use it, but my setup has gone bad, and I didn't really know what to do. So yeah, I don't know if I can really do it. Yeah, okay, there seems to be some movement. I'll let her be. Yeah, we can hide her, I think. Okay, let's start with a recap. Hello world, welcome back to Introduction to Machine Learning for Coders, us taking that course live together from fast.ai, that's taught by Jeremy Howard. And if you can remember, we finished lesson 6. I had to double check if we actually finished it or not, but apparently we did. We did the data products, list of data products, and the and the and now I'm distracted. Okay. Yeah, the live coding. We did the live coding. I can't do that. Quite interesting. Okay. It looks like I'm facing away. And then I think we will continue the live coding, which is the RF from scratch. And we'll start with gradient descent, which is very, very interesting, because it's like a ML2, it's like an intro to ML thing, which is what we're doing. So today we'll finish off our from scratch random forest interpretation. We'll also briefly look at the amazing Python. I don't know what that is. Library you can use to get the same speed as C. Oh, as in C and Python. Okay, now I get it. With minimal changes to your Python code. We then will start on the next stage of our journey, gradient descent, based methods such as logistic regression and neural network. Whoa. Okay, that's going to be cool. It's going to be so cool that you'll forget I have all those technical issues.
Welcome back. We're going to be talking today about random forests. We're going to finish building our own random forest from scratch. But before we do, I wanted to tackle a few things that have come up during the week, a few questions that I've had. And I want to start with kind of the position of random forests in general. So we spent about half of this course doing random forests, and then after today, the second half of this course will be neural networks, broadly defined. This is because these two represent like the two key classes of techniques which cover nearly everything that you're likely to need to do. Random forests belong to the class of techniques of decision tree ensembles, along with gradient boosting machines being the other key type, and some variants like extremely randomized trees.
They randomized trees
have the benefit that they're highly interpretable, scalable, flexible, work well for most kinds of data. They have the downside that they don't extrapolate at all to like data that's outside the range that you've seen, as we looked at the end of last week's session. Um, um, but they're a great starting point, and so I think there's a huge catalog of machine learning tools out there, and like a lot of courses and books don't attempt to kind of curate that down and say, like, for these kinds of problems use this, for these kinds of problems use that, finished, but they're rather like, here's a description of 100 different algorithms, and you just don't need them. Like, I don't see why you would ever use and support vector machine today.
Okay, so we don't need to memorize every type if we can use like a few. And also, I think my character is working better, so I'm glad I didn't remove her, but I hope she gets better. She has those glitchy moments.
For instance, like no reason at all I could think of doing that. People loved studying them in the 90s because they are like very theoretically elegant, and like you can really write a lot of math about support vector machines, and people did. But in practice, I don't see them as having any place. So there's like a lot of techniques that you could include in an exhaustive list of every way that people have looked at machine learning problems. But I would rather tell you like how to actually solve machine learning problems in practice. I think we're about to finish today the first class, which is one type of decision tree ensembles. In part 2, Yannet will tell you about the other key type there being gradient boosting, and we're about to launch next lesson into neural nets, which includes all kinds of GLM, ridge regression, elastic net, lasso, logistic regression, etc., are all variants of neural nets. Interestingly, Leo Breiman, who created random forests, did so very late in his life, and unfortunately passed away not many years later. So partly because of that, very little has been written about them in the academic literature. Partly because SVMs had taken over at that point. Other people didn't look at them, and also like just because they're like quite hard to grasp at a theoretical level, like analyze them theoretically. It's quite hard to write conference papers about them or academic papers about them. So there hasn't been that much written about them. But there's been a real resurgence, well, not resurgence, a new wave in recent years of empirical machine learning, like what actually works. Kaggle's been part of that, but also just part of it has just been like companies using machine learning to make shitloads of money, like Amazon and Google. And so nowadays, a lot of people are writing about decision tree ensembles and creating better software for decision tree ensembles like GBM and XGBoost and Ranger for R and scikit-learn and so forth.
Okay.
But a lot of this is being done in industry rather than academia.
Right.
But it's encouraging to see. There's certainly more work being done in deep learning than in decision tree ensembles, particularly in academia, but there's a lot of progress being made in both. If you look at like of the packages being used today for decision tree ensembles, like all the best ones, the top 5 or 6, I don't know that any of them really existed 5 years ago, maybe other than like sklearn or even 3 years ago. So yeah, so that's been good. But I think there's a lot of work still to be done. We talked about, for example, figuring out what interactions are the most important last week. And some of you pointed out in the forums that actually there is such a project already for gradient boosting machines, which is great, but it doesn't seem that there's anything like that yet for random forests. And, random forests do have a nice benefit over GBMs, that they're kind of harder to screw up, and easier to scale.
Easier to understand, to interpret.
So hopefully that's something that, this community might help fix.
That's so cool how much trust he has in his students.
Another question I had during the week was about the size of your validation set. How big should it be? So, like, to answer
So we have the 2080 of test and train, but validation.
this question about how big does your validation set need to be, you first need to answer the question, how accurate do I need, how precisely do I need to know the accuracy of this algorithm, right? So, like, if the validation set that you have is saying, like, this is 70% accurate, and if somebody said, well, is it 75% or 65% or 70%? And the answer was, I don't know, anything in that range is close enough. Like, that would be one answer. Whereas if it's like, is it 70% or 70.01% or 69.99%? Like, then that's something else again, right? So you need to kind of start out by saying, like, how accurate do I need this? So, like, for example, in the deep learning course, we've been looking at dogs versus cats images. Right. And the models that we're looking at had about a 99.4, 99.5% accuracy on the validation set.
Okay.
Okay. And our validation set size was 2,000. Okay. In fact, let's do this in Excel. That'll be...
Didn't we have a 5,050? It was 50K. Okay.
Be a bit easier. So our validation set size was 2,000, and our accuracy was 99.4%, right? So the number of incorrect is something around 1 minus accuracy times n. So we were getting about 12 wrong. Right. And the number of cats we had,
as in categories, not the feline,
is half. And so the number of wrong cats is about 6. Okay. So then, like,
can we have wrong cats? Are there wrong and right cats?
We run a new model, and we find instead that the accuracy has gone to 99.2%. Right? And then it's like, okay, is this less good at finding cats? And it's like, well, it got 2 more cats wrong. So it's like, probably not. Right? So, but then it's like, well, does this matter? Does 99.4 versus 99.2 matter? And if this was like, it wasn't about cats and dogs, but it was about finding...
Shoot. Why did I think it was categories? I thought it was categories because we had the whole cats thing. And we're actually talking about the feline. Good to know.
Finding fraud, right? Then the difference between a 0.6% error rate and a 0.8% error rate is like 25% of your cost of fraud. So, like, that can be huge. Like, it was really interesting, like, when ImageNet came out earlier this year, the new competition results came out, and the accuracy had gone down from 3%, the error went down from 3% to 2%. And I saw a lot of people on the internet, like, famous machine learning researchers being like, meh, some Chinese guys got it better from, like, 97% to 98%. It's, like, statistically not even significant, who cares, kind of a thing. But actually, I thought, like, holy crap, this Chinese team just blew away the state-of-the-art in image recognition. Like, the old one was 50% less accurate than the new one. Like, that's actually the right way to think about it, isn't it? Because it's like, you know, we were trying to recognize, you know, like, which tomatoes were ripe and which ones weren't. And, like, our new approach, you know, the old approach, like, 50% of the time more was, like, letting in the unripe tomatoes.
Okay. Okay, so we're looking at it based on, like, I get it, but I don't know how he's calculating that. I think I get it, I may not.
or 50% more of the time we were like accepting fraudulent customers. Like that's a really big difference. So just because like this particular validation set we can't really see 6 versus 8 doesn't mean that 0.2% different isn't important. It could be. So my kind of rule of thumb is that this number of like how many observations you're actually looking at, I want that generally to be somewhere higher than 22. Why 22? Because 22 is the magic number where the t-distribution roughly turns into the normal distribution. Right? So as you may have learnt, the t-distribution is the normal distribution for small data sets. Right? And so in other words, once we have 22 of something or more, it kind of starts to behave kind of normally in both senses of the words. Like it's kind of more stable and you can kind of understand it better. So that's my magic number. When somebody says, do I have enough of something? I kind of start out by saying, like, do you have 22 observations of the thing of interest?
Observations. Okay.
If you were looking at like lung cancer, and you had a data set that had like 1,000 people without lung cancer and 20 people with lung cancer, I'd be like, I very much doubt we're going to make much progress, because we haven't even got 20 of the thing you want. So ditto with the validation set. If you don't have 20 of the thing you want, then it's very unlikely to be useful. Or if like at the level of accuracy we need, it's not plus or minus 20. That's the point where I'm thinking like, be a bit careful.
So just to be clear, you want 22 to be the number of samples in each set, like in the validation, the testing.
Occurrences of the thing that you want. Target.
In the train, or
so what I'm saying is like if there's less than 22 of a class in any of the sets, then it's getting pretty unstable at that point, right? And so like that's just like the first rule of thumb. But then what I would actually do is like start practicing what we learned about the binomial distribution, or actually Bernoulli distribution. So what is the mean of the binomial distribution of
I have no idea.
n samples and probability p? N times p. Okay, thank you. N times p is our mean, right? So if you've got a 50% chance of getting ahead and you toss it 100 times, on average you get 50 heads. Okay. And then what's the standard deviation? NP1 minus p. Okay, so these are like two numbers. Well, the first number you don't really have to remember, it's intuitively obvious. The second one is one that try to remember forevermore, because not only does it come up all the time,
N is the number of the thing, and P is the probability. So NP is the mean, and NP1 minus P is the standard deviation. I'll try to remember it, but I won't make promises.
people that you work with will all have forgotten it. So you'll be like the one person in the conversation who can immediately go, we don't have to run this 100 times. I can tell you straight away.
That's so cool.
It's binomial. It's going to be NPQ, NP1 minus P. Then there's the standard error. The standard error is if you run a bunch of trials, each time getting a mean, what is the standard deviation of the mean? I don't think you guys have covered this yet. Is that right? No? So this is really important because this means like if you train 100 models, right, each time the validate.
Just like how we had multiple decision trees and we did the mean for each tree. Is that standard deviation of the mean?
Validation set accuracy is like the mean of a distribution, and so therefore the standard deviation of that validation set accuracy, it can be calculated with the standard error, and this is equal to the standard deviation divided by square root n. right? So this tells you, so like one approach to figuring out like, is my validation set big enough, is train your model 5 times with exactly the same hyperparameters each time, and look at the validation set accuracy each time, and it gives, there's like a mean and a standard deviation of 5 numbers you could use, or a maximum and a minimum you can choose. But to save yourself some time, you can figure out straight away that like, okay, well, I have a 0.99 accuracy as to whether I get the cat correct or not correct. So therefore, the standard deviation is equal to 0.99 times 0.01. Okay, and then I can get the standard error of that, right? So basically, the size of the validation set you need is like, however big it has to be, such that your insights about its accuracy are good enough for your particular.
And didn't we even do multiple validation sets, and then we looked at how accurate they would be, and then we chose one? I think it was randomly chosen.
Particular business problem. And so like I say, like the simple way to do it is to pick a validation set of like a size 1,000, train 5 models, and see how much the validation set accuracy varies. And if it's like, if they're all close enough for what you need, then you're fine. If it's not, maybe you should make it bigger, or maybe you should consider using cross-validation instead. Okay. So like, as you can see,
was that cross-validation what we did last time?
It really depends on what it is you're trying to do. How common your less common class is, and how accurate your model is. Could you pass that back to Melissa, please?
Thank you. I have a question about the less common classes. If you have less than 22, let's say you have one sample of something, let's say it's a face, and I only have one representation from that particular country, do I toss that into the training set and it adds variety? Do I pull it out?
If I have one occurrence in the whole database, then create synthetic data, is my advice, if you can.
Completely out of the data set, or do I put it in a test set instead of the validation set?
So you certainly couldn't put it in the test or the validation set, because you're asking, in general, because you're asking, can I recognize something I've never seen before? But actually, this question of like, can I recognize something I've not seen before, there's actually a whole class of models specifically for that purpose. It's called either one-shot learning, which is you get to see something once and then you have to recognize it again, or zero-shot learning, which is where you have to recognize something you've never seen before. We're not going to cover them in this course, but they can be useful for things like face recognition. Like, is this the same person I've seen before? And so generally speaking, obviously for something like that to work, it's not that you've never seen our face before, it's that you've never seen Melissa's face before, and so you see Melissa's face once and you have to recognize it again. So in general, your validation set and test set need to have the same mix or frequency of observations that you're going to see in production in the real world. And then your training set should have an equal number in each class. And if you don't, just replicate the less common one until it is equal. So this is, I think we've mentioned this paper before, very recent paper that came out. They tried lots of different approaches to training with unbalanced data sets and found consistently that oversampling the less common class until it is the same size as the more common class is always the right thing to do.
Oversampling, okay.
So you could literally copy, so like I've only got 1,000, 10 examples of people with cancer and 100 without, so I could just copy those.
Copy them and like rotate the image, flip it, discolor it. There's a thing where you stretch it. That's basically fake data, but in a good way.
10 another 90 times. That's kind of a little memory inefficient. So a lot of things, including I think sklearn's random forests, have a class weights parameter that says each time you're bootstrapping or resampling, I want you to sample the less common class with a higher probability. Or ditto if you're doing deep learning.
Okay, give it weight. Okay, that works too.
Learning, make sure.
I just realized my character is stuck. Oh, is she moving again? Oh, she's moving. Okay. She was stuck. She looked stuck for a bit. Anyway, I zoomed in just to see if it's working or not, but now it looks like it's working.
Your mini batch, it's not randomly sampled, but it's a stratified sample, so the less common class is picked more often. Okay. So let's get back to finishing off our random forests. And so what we're going to do today...
Yeah? Something tells me I want to stop. How long have we been streaming? Oh, only 38 minutes. Let's see what we have. Random forests. And then when do we start with a gradient descent? Because I want... It's fine. I mean, I'm really bothered by the issue of my character not being live and being very glitchy, but I still want to go on for another 15 minutes, so sorry about that. Forgive me for taking your time.
Is we're going to finish off writing our random forest, and then after today your homework will be to take this class and to add to it all of the random forest interpretation algorithms that we've learned.
Use it is basically what you were saying.
Okay, so obviously to be able to do that, you're going to need to totally understand how this class works. So please, ask lots of questions as necessary as we go along. So just to remind you, we're doing the bulldozers Kaggle competition data set again. We split it as before into 12,000 validation, the last 12,000 records. And then just to make it easier for us to keep track of what we're doing, we're going to just pick 2 columns out to start with, year made and machine hours on the meter. Okay. And so what we did
we have a subset of the data, okay.
Last time was we started out by creating a tree ensemble, and the tree ensemble had a bunch of trees, which was literally a list of n trees, where each time we just called create tree. Okay. And create tree contained a sample size number of random indexes. Okay. And this one was drawn without replacement. So remember, bootstrapping means sampling with replacement. So normally with scikit-learn, if you've got n rows, we grab n rows with replacement, which means many of them will appear more than once. So each time we get a different sample, but it's always the same size as the original.
Okay. You're taking it, but it's like you're taking the shortcut, if that makes sense, instead of the thing itself.
Data set. And then we have our...
Or actually, it's like you're pointing to it instead of taking it. Okay.
Set RF samples function that we can use, which does with replacement sampling of less than n rows. This is doing something again, which is it's sampling without replacement sample size rows, okay? Because we're permuting the numbers from 0 to self.y minus 1, and then grabbing the first self.sample size of them. Actually, there's a faster way to do this. You can just use np.random.choice, which is a slightly more direct way, but this way works as well. All right, so this is our random sample for this one of our n trees. And so then we're going to create a decision tree. And our decision tree, we don't pass it all of x, we pass it the specific...
Oh, okay, so this is our ensemble and this is our single tree, okay.
Specific indexes. And remember, x is a pandas data frame. So if we want to index into it with a bunch of integers, we have to use iloc, integer locations. Okay, and that makes it behave indexing-wise just like NumPy. Our y vector is NumPy, so we can just index into it directly. Right? And then we're going to keep track of our minimum leaf size. So then the only other thing we really need in Ensemble is some way to make a prediction. And so we were just going to do the mean of the tree prediction for each tree. All right, so that was that. And so then in order to be...
It was the same for the other random forest that we used. We were using the mean of the y.
able to run that, we need a decision tree class because it's being called here. And so there we go. Okay, so that's the starting point. So
starting point of having the tree and then the ensemble. Okay. We have X being our data, Y being our target, how many trees, sample size, and min leaf. Okay, and we're using it down here.
The next thing we need to do is to flesh out our decision tree. So the important thing to remember is all of our randomness happened back here in the tree ensemble. The decision tree class we're going to create doesn't have randomness in it.
Yeah, because it should rely on the before and next trees, right?
Okay, so right now we are building a random tree regressor, right? So that's why we are taking the mean of the tree, the outputs. If we were to work with classification, do we take the max? Like the classifier will give you either zeros or ones.
No, I would still take the mean. So each tree is going to tell you what percentage of that leaf node contains cats and what percentage contains dogs. So then I would average all those percentages and say across the trees, on average, there is 19% cats and 81% dogs. Good question. So, random tree classifiers are almost identical, or can be almost identical, to random tree regressors. The technique we're going to use to build this today will basically exactly work for classification. It's certainly for binary classification, you can do with exactly the same code. For multi-class classification, you just need to change your data structure so that like you have like a one hot encoded matrix or a list of integers that you treat as a one hot encoded matrix. Okay, so our decision tree, so remember our idea here is that we're going to like try to avoid thinking. So we're going to basically write it as if everything we need already exists. Okay? So we know from when we created the decision tree, we're going to pass in the X, the Y, and the minimum leaf size. So here we need to make sure we've got the X and the Y and the minimum leaf size. Okay. So then there's one other thing, which is as we split our tree into subtrees, we're going to need to keep track of which of the row indexes went into the left-hand side of the tree, which went into the right-hand side of the tree.
Oh, okay, so that we can use and talk to them. Okay, this is not easy.
Tree. Okay, so we're going to have this thing called indexes as well, right? So at first, we just didn't bother passing in indexes at all. So if indexes is not passed in, if it's none, then we're just going to set it to the entire length of y. Right, so np.arange is the same as just range in Python, but it returns a NumPy array. Right, so the root of a decision tree contains all the rows. That's the definition, really, of the root of a decision tree. So all the rows is row 0, row 1, row 2, etc., up to row y minus 1. Okay, and then we're just going to store away all that information that we were given. We're going to keep track of how many rows are there and how many columns are there. Okay. So then every leaf and every node in a tree has a value. It has a prediction. And that prediction is just
how are we saving this? Because we have the list of indexes, but we're not saving it like a tuple?
Equal to the average of the dependent variable. Okay, so every node in the tree, y indexed with the indexes is the values of the dependent variable that are in this branch of the tree, and so here is the mean. Okay? Some nodes in a tree also have a score, which is like how effective was the split here, right? But that's only going to be true if it's not a leaf node, right? A leaf node has no further splits. And at this point when we create a tree, we haven't done any splits yet, so its score starts out as being infinity. Okay? So having built the root of the tree, our next job is to find out which variable should we split on and what level of that.
Whoa, this is like a real tree, huh? Okay, we're in the root tree. Okay.
Variable should we split on. So let's pretend that there's something that does that. Find var split. So then we're done. Okay, so how do we find a variable to split on? So, well, we could just go through each potential variable. So C contains the number of columns we have. So go through each one and see if we can find a better split than we have so far.
That's funny. Find one to split on and then find a better thing to split on. That's quite funny.
On that column. Okay. Now notice this is like not the full random forest definition. This is assuming that max features is set to all, right? Remember, we could set max features to like 0.5, in which case we wouldn't check all the numbers from 0 to C. We would check half the numbers at random from 0 to C. So if you want to turn this into like a random forest that has the max features support, you could easily like add one line of code to do that. But we're not going to do it in our implementation today. So then we just need find better split. And since we're not interested in thinking at the moment, for now we're just going to leave that empty.
I love it. My style of coding.
All right. So the one other thing I like to do with my kind of, when I start writing a class, is I like to have some way to print out what's in that class. Okay. Right? And so if you type print followed by an object, or if at Jupyter Notebook you just type the name of the object, at the moment it's just printing out underscore underscore main underscore underscore dot decision tree at blah blah blah, which is not very helpful, right? So if we want to replace this with something helpful, we have to define the special Python method name dunder repra.
Repra? As in reprint?
To get a representation.
Representation, okay.
Of this object. So when we basically...
In Java, there's the toString function that you can print whatever you like. But I mean, so is that the same idea? I don't think so. Because then it prints whatever you want of like an object. But this is basically like having get and set for the attributes, right?
Just write the name like this. Behind the scenes it calls that function, and the default implementation of that method is just to print out this unhelpful stuff. So we can replace it by instead saying, let's create a format string where we're going to print out n and then show n and then print val and then show val. Okay, so how many rows are in this node and what's the average of the dependent variable? Okay. Then, if it's not a leaf node, so if it has a split, then we should also be able to print out the score, the value we split out, and the variable that we split on. Now you'll notice here, self.isLeaf. isLeaf is defined as a method, but I don't have any parentheses after it. This is a special kind of method called a property. And so a property is something that kind of looks like a regular variable.
Okay. We don't have that in other languages, I think. Or maybe I just don't know.
But it's actually calculated on the fly. So when I call isLeaf, it actually calls this function, right? But I've got this special decorator property, okay? And what this says is basically you don't have to include the parentheses when you call it, okay? And so it's going to say, all right, is this a leaf or not? So a leaf is something that we don't split on. If we haven't split on it, then its score is still set to infinity. So that's my logic. Does that make sense? So this at notation is called a decorator. It's basically a way of telling Python more information about your method.
Yeah, it's metadata. Just like how in Java we have override, I think. Like, even in C# there are like a lot of stuff you can put on top. Are they all called decorators?
Does anybody here remember where you have seen decorators before?
I just answered you. Hey.
Can you pass it over here? Yeah, where have you seen decorators
Flask.
before? Tell us more about Flask and how it uses
It
decorators.
was the app route.
Yeah. What does that do?
Isn't it? I've used Flask. Does it? Yeah, no. Okay, I'm not remembering correctly. Okay.
That I forgot.
Okay.
I don't
So
know how to describe it.
no worries. So Flask. So anybody who
Isn't it the path? No, like URL.
who's done any web programming before with something like Flask or a similar
Oh shoot! I have the. Oh, now I remember where I've used Flask. Yes, it should be the URL. I think.
framework, would have had to have said, like, this method is going to respond to this bit of the URL and either to post or to get, and you put it in a special decorator. So behind the scenes, that's telling Python to treat this method in a special way. So here's another decorator, okay? And so, if you get more advanced with Python, you can actually learn how to write your own decorators, which, as was mentioned, basically insert some additional code. But for now, just know there's a bunch of predefined decorators we can use to change how our methods behave. And one of them is at property, which basically means you don't have to put parentheses anymore.
Cool.
Which, of course, means you can't add any more parameters beyond self. Yep.
Why, if it's not a leaf, why is the score infinity? Because doesn't infinity mean you're at the root? Why? If
No,
you're not
infinity
at the
means
root?
that you're not at the root. It means that you're at a leaf. So the root will have a split.
And we'll have value score because it's split. But leaves haven't split, so they don't have a score. Yes?
Assuming we find one.
Yeah.
Right? Everything will have a split till we get all the way to the bottom,
Yeah.
the leaf. And so the leaves will have a score of infinity because they won't split. Great. All right.
All right. Now it's time for me to leave. Apologies about the character. She is having issues today. I don't know when we'll fix it. So, yeah, the future looks bleak. And so I thank you for your patience and for being here for this chill stream. I hope you learned something with me. I like looking under the hood of the random forest. That's pretty cool. Like, now we have to decide on what to split and all that, so that's pretty interesting. Yeah, my character's stuck, so sorry about that. And I hope we can continue. We're in lesson 7. Can you believe that? I didn't trust myself to go this far, and here we are. So I do really appreciate your support. And here, my character is moving. Oh wow, she's almost real time. Okay. I will come back tomorrow as per schedule, even though my schedule was I shouldn't have streamed today, so yes. I'll try to fix the character issues, but like I said, the current future looks bleak unless there's an update to Android Studio. So thank you for being here. Apologies for the technical issues, even though the stream didn't have like cut off issues, so that's cool. But yeah, sorry about the character. I hope we can continue learning together. Let me know if you have any notes or questions. And yeah, I'm gonna end the stream in 5, 4, 3, 2, 1. Thank you for being here. Bye.